Alrighty. Okay, let's see what we have here. That may be hard. Number of paths with max score. You're given a square board of characters. You can move on the board starting at the bottom right square marked with the character S. You need to reach the top left square marked E. The bottom right, top left, okay. The rest of the squares are labeled either numeric 1 to 9 or an obstacle X. In one move, you can go up, left, right, up, left, or up, left. Diagonally, only if there's no obstacle there. Return a list of two integers. The first integer is the maximum sum of numeric characters you can collect. And the second is the number of such paths that you can take to get that sum. Modulo 10 to the 9th plus 7. In case there's no path, return 0, 0. So from bottom right, this would be like S. So start to exit. The maximum path would be like go up 2, go up 3, go left 2. That gives you 7, and there's one path. Okay, 7, 1. Here you would go, because there's two paths, go left, left, up, up. So 1, 2, 1, 1. No, 1, 2, 1 is 4. Or up, up, left, 1, 2, 1. And this one, there's no way because there's just obstacles blocking second row. Okay. Seems simple enough, I guess. The highest path cost and the number of ways to do it. Okay. So if I think about it, is kind of weird to be able to do diagonals. Generally in a problem like this, diagonals are not a possible movement. It's either up or left to make it kind of consistent for your kind of diagonal position after X moves or after some number of moves. But with diagonals, this can be faster and possibly faster. Actually, why would anyone ever do a diagonal? You would ever only do a diagonal if you can't move, like, if you're blocked from moving, like, if you're moving diagonally top left, you would prefer to do like left up or up left, because that would give you a higher score. But if you're blocked from doing that, then you'd have to go diagonally. But otherwise, diagonally is just going to be strictly less. How to do this? Seems like it'd be something like a breadth first search. You have a position in a stack or queue that you're processing. And that position either goes left, up or up left. I guess. What does this mean? Let's do example 1. Let's say there was something here, like let's say there was a 1 there. Or 3. Or at this position, push these to position on the stack. When you're at a certain position, you push the neighboring position on the stack. I don't think that's right. So if your position S, the starting position, you move either left up, or up. Let's say you process left. Left can go left or up. And then you process up, maybe. Or you process this. Oh, what to do. Maybe. Um, hmm. Maybe I should. Maybe I should process everything on a certain diagonal. So I would use a. Is that a heap? If I try to process on a certain diagonal, kind of have it sort. Actually, maybe I just do for loops. Iterate over every position in the grid, in the board. So process this position, this position, this position. Process every position. I assume that's probably fine. Yeah, the board's like 100 by 100. Process every position. Only worry about the highest path, the highest path sum up to that position, and the count of the things with that path sum. and then roll that over, I think. Okay. So let's say I store um, paths, which is going to be a 2D array where the um, input is the position, or the input is like the indices equals position of board, and the value at the index is the tuple that is the highest path score, highest path sum, and the count of the number of ways to do that. Okay, so I think I just need to generate the paths 2D array. Say 0, 0. Need the sizing here, rows, columns. I guess this is a square. So n is the length of board. And then 0, 0 for everything in range n for everything in range n. I don't know if I need a double underscore here. Just make sure that this looks right. Okay, it's 2D array, 3 by 3, 0, 0, every element in the 2D array. That's right. Okay. So I'm going to go ahead and work uh, from each position. I think I want to convert board to be like a 2D. I want to convert board into a 2D integer array. Okay, let's say board cost. How to do this here. For every, let's say, row in the board, which is a string. Guess I convert it into a, so let's say for every digit in that row string. If the digit is a character, is an integer. Now to check if string is numeric Python. S is digit. Use a try except is digit. A digit is digit. Then I guess I just cast it. Int board cost append integer of the digit, else board cost append. Actually, this should be a separate thing. Should be an array of current digits of the current row. And I'll do 0 for x. Actually, maybe I should do -1. -1 for obstacles. And then just convert this thing or append this thing. Okay, -1, 2, 3, 2, -1, 2, 1, 2, -1. Okay. I think I might want to change the first and last for the exit and starting to be especially 0, maybe. So board cost at 0, 0 equals 0. Board cost at -1, -1 equals 0. Oh, that's fine. Before I forget, I'm going to do return answer mod. I guess answer starts with 0. Actually, that does make sense there because it has to be an array. The answer needs to be the count. No, I guess it needs to be answer cost and answer count. Okay. Well, I can make this into one line. All right, so now starting at the bottom right position, I iterate over the positions of the board diagonally. Using a nested for loop, I think. So nested for loop should be better about. I should have more practice with this iteration type. For n minus 1. say P in range n minus 1, or let's say R, I guess. Row iterating backwards, column iterating forwards, because I want to iterate from like this position, which is row n minus 1. Maybe I should be doing diagonal. The row starts at n minus 1. So it's going to, like it needs to iterate over like 1, 2, 3, and even type it. It's be like 0, 1, 2, 3, 4, 5. Maybe it should be based on diagonal as the outer loop. Diagonal is defined by row plus column. So it's rows 2, columns 2. So it's 2 plus 2 is 4. Diagonal 0, 1, 2, 3, 4. So for diagonal in 2 times n minus 2, maybe, is the starting diagonal. And then I just need to find the correct position. Okay. For diagonal in range, I think it's 2 times n minus 2, because if this was a 4 by 4, then your starting diagonal will be 0, 1, 2, 3, 4, 5. That's not right. How many diagonals are here? 2 times n 0, 1, 2, 3, 4, 5, 6. If it's a 4 by 4. Okay, yes, 2 times n minus 2. So the diagonal is from that value to 0, decrementing. And the first position is going to be like row 0 or row n minus 1 or column 0. Row n minus 1 or column row n minus 1 or row diagonal. I see. Okay. R equals diagonal if the diagonal is greater than or equal to n divided by greater than or equal to n, else it's equal to the, no, sorry, it's equal to n minus 1. So we start this bottom row if it's a higher diagonal. Diagonal is greater than n. Well, it's just the diagonal itself is the same as the row. And then the column is whatever is the complementary value, I think. Because everything in the diagonal has a row plus columns the same. Like this is 5, 1, and this is 4, 2. This position is 5, row 5, column 1. This position would be row 4, column 2. 0, 1. Actually, no, sorry, this position is row 3, column 2, which adds up to 5. Yep, row 3, column 2. This one will be row 2, column 3. That's the 5. So the column is equal to diagonal minus row. And then that's the initial. Maybe I got this R0. And then the number of elements in this diagonal is going to be the inner for loop, which should be how far this is from the ends, how far diagonal is from the end diagonal. Diagonal count is needs to be 1, then 2, then 3, then 2, then 1. Or 0, 1, 2, 2, 1, 0, 1, 2, 2, 1. The number elements here 0, 1, 2, 2, 1, 0, 1, 2. So I can do the minimum of the diagonal and oh boy, 0, 1, 2, 2. The minimum of the n minus diagonal or diagonal minus n. Oh, n minus diagonal or n. Yeah, something like min of n minus diagonal or diagonal plus 1 maybe. Or is it n minus, or 2n minus diagonal? 2n minus 2 minus diagonal? Yeah, I think that's right. Okay, so for everything in this diagonal count, let's say the position is equal to the row and column is R0 minus K and column 0 plus K is the current position in the diagonal. Okay. So it starts out with the starting position. And then it needs to check every movement position from here. So it's going to be a step. It's either going to move one less on the row, 0 in the column, one less on the column, 0 in the row, and one less in the column, one less in the row. Maybe I need to put out of bounds on this board. I think I will actually. Yeah, I think I will. So I'm going to add an extra boundary on the right side. Then I want to add an extra boundary on the bottom side. And then this should be now -2, -2 to position this. Just double checking. This is adding a -1 boundary. Okay, yeah, so it's -1, kind of an extra boundary. My starting position is still this position right here. Because I'm going to ignore everything that moves into an obstacle or a -1 cost. Or a -1 score, I guess. Okay, so for every dr, dc in the deltas, and our new row, new column is row plus dr, c plus dc. If board costs at nr and c is equal to -1, then continue, skip it. I guess I need to evaluate from the current position first. So I need to go, let's say, this shouldn't be called costs. This is actually the points, or I guess I'm just maximizing costs. I guess cost is equal to cost and count is board costs at the current position. I guess I can skip this if the count is 0. That's not true. Oh, I'm confusing cost with pass. Yeah, this should be pass. What am I doing? I think the first path should start with the 1, right? So pass at -1, -1. Should it be 0 cost? One way to do that. Yeah. Okay, so cost and count is from the current position. Then for every neighboring direction, go to that neighboring cell. If it's an obstacle, skip it. Otherwise, it's a possible movement, I guess. Actually, if the count of the number of ways of getting here is 0, then skip it. And then for every neighboring position, I need to update the path from here to that position. Adjacent cost, adjacent count equal diagonal or paths to that position. If so, this has to be a higher cost. If the current cost plus the board costs at that position is less than the adjacent cost. So there's a different way of getting there. That's higher. Then skip this. Else, if it's the same, then increase it. Increase the count. Oh, it's just going to be the new cost of going this current path. I don't think this should be called cost. It should just be called cost. And just use the So you're going to use just one? I think so, right? I should just use this current method. Current count to get to this thing, which might be one. Okay, I think that makes sense. Okay. So I move from every position, check every neighboring position, update the best path to that position, including the count. And then I just return, right? I think maybe at that point, I'm just storing everything inside the pass array. So this should be pass of 0, 0. This is going to be a tuple. So entry 0. And then pass of 0, 0, 0. Entry 1 of the tuple. Okay. Oh, this should be R0. Misspelled board cost. That's kind of a slow time. All right. Well, it's an answer. Only 25 test cases. Okay, let's think about this. Um, so I'm going over my paths. Starting path has 0 cost one way. have a board cost, which translates the board into something that's more usable. And then when I do the translation, I convert the string into digits, integer digits, -1 for x's for obstacles, manually change the exit and starting as 0 cost. Also manually kind of add in a -1 obstacle boundary to the board so that when I index into a position that's off the board, it's going to be treated like an obstacle. I have my deltas, which is moving left, right, and or left, up, and up, left. Then I have my diagonal. So I'm iterating over all the positions, starting with the diagonal positions, or iterating through the diagonal positions. I think that's fine. Don't think this is particularly slow at all. A is the offset from the starting position to the diagonal. Or 0, C0 is the starting position, the diagonal. So like diagonal 6 starts at this position, diagonal 5 starts at this position, 4, 3, 2, 1, 0. So the higher diagonal values are going to have n-1 as the starting row. Otherwise, the row is actually the diagonal value. And the column is just the complement of the summation value to diagonal. Diagonal count is just that value. And then for every offset from the initial position in the diagonal, get the path to that position. If there's no paths, then we skip it. Then if there are movements left top or top left from this, skip it if it moves to an obstacle. Otherwise, evaluate it. Smaller than the adjacent cost already, then it's not going to work. Equal to, then it's going to up the count. Otherwise, it's going to say this is the best way. I mean, kind of slow, right? All right, well, gave a run through, but didn't come up with anything. So for your summary, not really optimized, I guess. But in general idea for solution is one kind of, this is kind of a kind of a setup. Convert the board array into kind of a 2D integer array of values, right? Converting like a character 1 to a integer 1. E and S are 0 values and X's are -1 for special points. And then have a 2D array, which I kind of called path, which track the highest path score, which track for each position on the board, highest path score, and to that position, and the count of those paths. So that's going to be basically stores a tuple. So it's a 2D array of tuples, right? So it's this thing right here, paths. Also note that for the setup and above also included an extra kind of row / column of -1s to serve as boundary obstacles to prevent kind of out of bounds kind of pathing, because -1 is going to be treated as kind of the right side of the 2D array in Python. And then, so here I have a tricky step, or for me anyways, is to set up kind of a nested for loop that iterates over the positions of the board in a kind of diagonal pattern. So it's going to like iterate over, it's going to be something like this is 0, then 1, then 2, 3, 4, 5, 6, 7, 8, so something like that. So set up, basically set up a nested for loop where outermost is the diagonal and inner loop iterates over the elements of that diagonal. So in theory, technically, the 0 is on the same diagonal as on the singular diagonal. 1, 2 is on, well, I called 0 on diagonal 5, 1, 2 in diagonal 4, 3, 4, 5 diagonal. Actually, that should be diagonal 2, 6, 7 on diagonal 1, 8 on diagonal 0. So that was like this setup here. R0, 0, 0 is the first position of the diagonal elements. And then for while iterating over all positions in the board following diagonal pattern, for each position, it kind of costs or cost / count, highest cost value to this position and the total number count for that value, and then iterate over all or the 3 directions from that position. updating the paths for those adjacent positions. So once you have a position and you know the cost and the count for that position, you iterate over a kind of array, or in this case, a set of delta row, delta columns. This is going left, this going up, this going up left. Find the new position. If the new position is an obstacle, then skip it. And then check the cost and the count of that position if it's already some value. And if the current way to this position plus the kind of points to get to that new position is not better than whatever is a higher score that's already found to that position, then skip. Otherwise, like update. And then basically return the for loops. The first position should have the info for the answer. Highest points, then highest count and total count. Return those values. All right, time collectively is going to be O of n squared. Since you need to iterate over each position, and each position basically does constant work. Like you're doing the 3 neighbors. Space complexity is going to be O of n squared. Since you're storing basically some extra information for each position on the board. All right, cool beans.